Everything we think we know about the universe's beginning might be wrong. The story of the Big Bang is just the surface of a far deeper mystery. We are going to unearth 25 forgotten facts that completely challenge our cosmic story. By the end, you will see the origins of everything in a startling new light. We will confront stars older than time itself and grapple with a universe that is mostly invisible. What hidden truth about our beginnings is the most difficult to believe? Our first forgotten fact begins with a cosmic contradiction. The universe, according to our best measurements, is about 13.8 billion years old. Yet, when we peer into the ancient neighborhoods of our own galaxy, we find stars that seem to defy this timeline. These are the residents of globular clusters, dense balls of hundreds of thousands of stars that orbit the galactic core like ancient sentinels. By studying the faint, cooling embers of white dwarf stars within them and analyzing the precise chemistry of their oldest members, astronomers have calculated ages. Some of these stellar fossils appear to be over 14 billion years old. That is older than the universe itself. This is not a small rounding error, it is a fundamental paradox. How can something inside the universe be older than the universe? This discrepancy strikes at the heart of our standard model of cosmology, known as the lambda-CDM model. One key piece of that model is the Hubble constant, the number that describes how fast the universe is expanding today. Its value directly tells us the universe's age. If the stars are truly older, it might mean our expansion rate is wrong, or that our understanding of stellar physics in those first epochs is incomplete. Perhaps the universe underwent a strange, slow-motion phase at its birth, making it effectively older than the expansion story suggests. This single forgotten fact, written in the light of the oldest stars, tells us our cosmic clock may need a serious recalibration. That paradox of ancient stars points to a flaw in our timeline, but the second forgotten fact shatters our timeline entirely. The most common question about the universe's birth is also, in a profound way, meaningless. We instinctively ask what happened before the Big Bang. The startling answer from our foundational physics is there was no before. Time, as we understand and experience it, is not a universal backdrop that existed forever. It is a property that emerged from the Big Bang itself. Think of it like asking, what is north of the North Pole? The question sounds logical, but the framework of geography breaks down. North only has meaning relative to a point on the globe. At the pole itself, every direction is south. The concept of further north ceases to exist. In the same way, our concept of before requires a flowing river of time to make sense. At the moment of the initial singularity, that river, according to Einstein's theory of general relativity, simply did not exist. The singularity wasn't a point in space. It was a point where all the laws of physics, including the dimension of time, ceased to function. Asking what came before the Big Bang is like asking what sound is north of the North Pole. It is a question that loses its meaning within the context of the event. This conclusion is so uncomfortable that it has spawned entire branches of cosmology looking for an escape. Some theories, like the cyclic model, propose our universe is just one in an endless series of expansions and contractions, a cosmic heartbeat where each Big Bang is preceded by a big crunch. Others suggest our universe is a bubble in a much larger, timeless multiverse. But within the strict confines of the standard model, the origin point remains a hard boundary to our reality. Time itself is a creation of that event, a forgotten fact that tells us our most basic intuition about cause and effect may not apply to the ultimate beginning. If time itself began at the Big Bang, then our third forgotten fact completely redefines the stage upon which everything unfolded. We have a deeply ingrained mental image of the Big Bang as a colossal explosion, like a cosmic firecracker detonating in an empty, pre-existing void. This picture is fundamentally and spectacularly wrong. The Big Bang was not an explosion in space. It was the explosive expansion of space itself. There was no center, no epicenter where the blast happened. Instead, every single point in our observable universe today, every galaxy, every star, and the space between them, was once compressed into the same unimaginably hot, dense state. To visualize this, think of the surface of a balloon covered with tiny dots. As you inflate the balloon, every dot moves away from every other dot. No dot is the center of the expansion. The center is inside the balloon, a dimension the dots on the surface cannot perceive. In our universe, we are like those dots. We see all other galaxies rushing away from us, which might make us feel special. But an observer in any other galaxy would see the exact same thing, everything rushing away from them. The space between the galaxies is what is truly stretching. This means the location of the Big Bang is not a point out there in the distant cosmos. It is right here and everywhere. It happened in the room you are sitting in, and in the most distant quasar we can see. We are inside the aftermath of that event. This forgotten fact forces us to abandon the idea of a cosmic center and accept a far stranger reality, that the entire fabric of our existence is the product of that initial stretching. That everywhere and nowhere nature of the Big Bang leaves us with a fossil, a ghostly afterglow that we can actually see. This cosmic microwave background radiation is the oldest light in the universe, a snapshot of the cosmos when it was just a hot, dense fog about 380,000 years old. It is our most powerful evidence for the Big Bang, and we have mapped it in exquisite detail. But within that map lies our fourth forgotten fact, a pattern so strange and unsettling that cosmologists gave it a darkly humorous name, the axis of evil. When scientists created a full sky map of the subtle temperature variations in this ancient light, the hot and cold spots should be scattered randomly like a cosmic static. The universe should have no preferred direction, yet the map revealed something shocking. These spots show a curious alignment that eerily corresponds with the plane of our own solar system and the direction of the Earth's motion through space. It is as if the entire universe has a faint fingerprint, and that fingerprint is suspiciously oriented around us. The statistical odds of this happening by pure chance are astronomically low, less than 1 in 1,000. This is not just a minor curiosity, it is a profound anomaly that cuts to the core of the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, meaning it looks the same in all directions and from every location. The axis of evil suggests for a terrifying moment that we might somehow be in a special place, a notion modern science had thoroughly dismissed. Could it be a flaw in our instruments, a contamination from our own galaxy? Possibly, but exhaustive checks have not made it disappear. Some theorists whisper about pre-Big Bang structures imprinting themselves on the newborn cosmos, or even the influence of a neighboring universe brushing against our own in a vast multiverse. This forgotten fact is a quiet crack in the foundation of cosmology, a whisper from the first light that we are not seeing the whole picture, and that our place in the cosmos might be stranger than we ever dared to believe. The whispers of the axis of evil are not the only anomaly written in the ancient elements. Our fifth forgotten fact is etched into the very atoms of the oldest stars, and it tells us that the first few minutes of cosmic creation did not go according to plan. In the searing heat of the early universe, just minutes after the Big Bang, protons and neutrons fused in a frantic burst of creation known as Big Bang nucleosynthesis. This process forged the universe's first atomic nuclei, primarily hydrogen and helium, with trace amounts of two other light elements, deuterium and lithium-7. The amounts produced are exquisitely sensitive to the conditions of the early cosmos, its density and expansion rate. For deuterium, the predictions match what we observe almost perfectly, a triumph for the Big Bang model. But for lithium-7, the story breaks down. The universe, according to our most precise calculations, should have created about 3 times more lithium-7 than we actually find when we analyze the atmospheres of the most ancient, pristine stars in our galaxy. These stars are our time capsules, formed from nearly pure Big Bang material, so their composition should mirror those first moments, yet the lithium is missing. This is not a small accounting error, it is a glaring deficit that has persisted for decades, stubbornly resisting every attempt at explanation. Could ancient stars somehow destroy or hide lithium deep in their cores over billions of years? Possibly, but models of stellar physics struggle to make this work. Could our understanding of nuclear reaction rates in that primordial inferno be incomplete? That is a more unsettling possibility, implying a gap in our knowledge of fundamental physics under conditions we can never recreate. The lithium problem is a quiet but persistent thorn in the side of cosmology, a forgotten fact that suggests the recipe for the universe, written in its first 3 minutes, might have a missing ingredient or a misprinted instruction. The lithium problem hints at a flawed recipe, but to understand why, we must rewind the clock further, into the most extreme and mysterious moment of all. The first second of the universe was not a single event, but a breathtaking cascade of cosmic phases, each more alien than the last. Our story begins at time zero, the moment of the initial singularity. But our physics utterly fails here. This is the Planck epoch, a duration so inconceivably short it is 10 to the negative 43 seconds. At this scale, the universe was smaller than a single atom, and all 4 fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. We have no theory that can describe this state. It is a realm of pure quantum gravity, a complete mystery. As the universe expanded and cooled past that impossible threshold, the first great separation occurred. Gravity split off from the other 3 forces. This marks the grand unification epoch. For another sliver of time, the remaining 3 forces, electromagnetism and the nuclear forces, remained as one. The energy of this unified field was unimaginable, and it may have seeded the universe with its most fundamental particles. Then, at around 10 to the negative 36 seconds, something extraordinary happened. The universe entered a phase called cosmic inflation. A strange field, known as the inflaton field, is thought to have dominated the cosmos. It possessed a peculiar property, repulsive gravity, causing space itself to expand faster than the speed of light. In less than a blink, a region smaller than a proton was stretched to a size larger than our entire observable universe today. This explosive growth solved major puzzles, like why the cosmos is so uniform and flat. More importantly, inflation stretched tiny quantum fluctuations in that field into macroscopic ripples. These ripples became the seeds for all future structure, the galaxies, stars, and planets we see today. Without inflation's furious stretch, the universe might have remained a smooth, empty, and dull place. Inflation ended as abruptly as it began, around 10 to the negative 32 seconds. Its immense energy decayed, flooding the universe with a hot soup of particles and radiation. We now enter the quark epoch. The universe is still far too hot for protons and neutrons to form. Instead, it is a seething plasma of quarks and gluons, the fundamental building blocks of matter, all moving freely in a dense, primordial fire. The strong nuclear force, which normally binds quarks together, is still too weak to overcome the intense thermal energy. This quark-gluon plasma is a state of matter we can now briefly recreate in particle colliders, giving us a tiny window into this ancient inferno. As the expansion continues, the universe cools further. Around 1 microsecond after the Big Bang, the temperature finally drops enough for the strong force to take hold. Quarks and gluons become confined, locking together into the first protons and neutrons. The stage is now set for the nuclear fusion we discussed earlier, the forging of the first light elements. all of this, from a unified superforce to a universe filled with tangible matter, happened before you could snap your fingers. The entire architecture of our reality was decided in that first, fleeting second, a forgotten fact written in the laws of physics themselves. That furious expansion of space in its first instant did more than just stretch the universe, it shook the very fabric of reality. This leads us to our seventh forgotten fact. Cosmic inflation left permanent ripples in spacetime itself. The same quantum fluctuations that seeded galaxies also generated something far more profound: primordial gravitational waves. Imagine the infant universe not as a smooth, placid sea, but as a turbulent, frothing ocean during a storm. Inflation would have stretched those quantum ripples in the fabric of space-time, amplifying them into vast, gentle undulations that propagate through the cosmos. These are not waves of light or matter, they are waves in the geometry of the universe, distortions that literally stretch and squeeze space as they pass by. Their detection would be the ultimate smoking gun for inflation, a direct signal from that unimaginably violent first fraction of a second. So how do we hunt for such an elusive ghost? We look for its fingerprint in the oldest light we have, the cosmic microwave background. As this ancient light traveled through the universe, the passing gravitational waves would have subtly twisted its polarization, the orientation of its light waves. This creates a distinctive, swirling pattern in the polarization map, known as a B-mode pattern. Finding this specific signature is the holy grail of modern cosmology. Experiments like BICEP, located at the South Pole to take advantage of the cold, dry air, have been scanning the sky with incredible sensitivity. In 2014, there was a moment of tremendous excitement when the BICEP team announced a possible detection. The scientific world held its breath. Unfortunately, further analysis revealed the signal was largely contaminated by interstellar dust within our own Milky Way galaxy. It was a sobering lesson in cosmic humility. The hunt, however, is far from over. New generations of ground-based telescopes and future space observatories are being designed with even greater precision, armed with better knowledge of galactic dust. They are patiently listening for the faintest echo of inflation's birth cry. If they succeed, it will be one of the greatest discoveries in the history of science, confirming our wildest theories about the universe's first moments and opening a direct window to an epoch before time had any real meaning. The hunt for gravitational waves is a search for echoes from the universe's violent birth, but it forces us to confront a far more unsettling reality. Our eighth forgotten fact is this: everything we have ever seen, every star, every galaxy, every planet, and every one of us, is nothing more than a cosmic afterthought. All the atoms that make up the known universe, the tangible stuff of reality, account for less than 5% of its total contents. The remaining 95% is a profound and humbling mystery, composed of two invisible, unknown entities: dark matter and dark energy. Our entire origin story is not just dominated by the Big Bang, but by these two shadowy forces we cannot see or directly touch. Dark matter was the first ghost to reveal itself. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. By measuring how fast individual galaxies were whirling around the cluster's center, he could calculate how much total mass was needed to hold them together with gravity. The answer he got was staggering. The visible mass of all the stars and gas was hundreds of times too small to provide the necessary gravitational glue. Something invisible, something that did not interact with light at all, was providing the extra gravity. He called it Dunkel Materie, dark matter. Decades later, Vera Rubin provided even more compelling evidence by looking at single spiral galaxies. She found that stars at the outer edges of these galaxies were orbiting just as fast as stars near the center. According to the laws of gravity, these outer stars should be moving much more slowly, like planets farther from the sun. The only explanation: a vast, invisible halo of dark matter enveloping each galaxy. providing the extra gravitational pull to keep those stars from flying off into the void. We now believe this dark matter scaffold forms the underlying skeleton of the cosmos. It clumped together first after the Big Bang, and its gravity then drew in ordinary atoms to form the galaxies and stars we see. We are literally living in the aftermath of a shadowy architecture we can never see. But dark matter, as strange as it is, only makes up about 27% of the universe. The real shock came at the turn of the millennium. Two independent teams of astronomers were measuring the distances to far-off supernova, using them as cosmic mile markers to track how the universe's expansion has changed over time. Everyone expected to find that the expansion was slowing down, gradually coasting under the steady pull of gravity from all the matter in the cosmos. Instead, they discovered the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is pushing galaxies apart with ever-increasing force. This something was named dark energy, and it constitutes a staggering 68% of the universe. Dark energy is not a clumpy substance like dark matter. It seems to be a property of empty space itself. As the universe expands, more space is created, and with it, more of this repulsive energy, leading to a runaway acceleration. This means the fate of the cosmos is not a gradual fade or a dramatic crunch, but a cold, lonely drift into infinite separation. The most dominant force shaping the universe's destiny is this mysterious anti-gravity, and we have almost no idea what it is. So when we tell the story of our origins, we are focusing on the 5%, the luminous footnote. The true authors of the cosmic story, the dark matter that sculpted it and the dark energy that now controls its fate, remain complete enigmas. Our universe is a ghost ship sailing on an invisible sea, steered by forces we are only beginning to name. Dark energy and dark matter may dominate our universe, but the story of life and intelligence is written in that tiny 5% of ordinary stuff. This leads us to a forgotten fact that is not about what is out there, but about what we do not hear. The universe is profoundly silent. This is the heart of the Fermi paradox, a simple, haunting question posed by physicist Enrico Fermi over lunch one day in 1950. Given the vast age and size of the cosmos, with hundreds of billions of stars in our galaxy alone, many of which are older than our sun, where is everybody? If life and intelligence are at all common, the galaxy should be teeming with civilizations. We should see their engineering projects, hear their broadcasts, or find their artifacts. Yet we detect nothing but cosmic static. The silence is deafening. The roots of this great silence may stretch all the way back to the universe's origins, written into the very conditions of our birth. First, consider the timing. Our universe is 13.8 billion years old, but for most of that history, it was utterly inhospitable to complex life. The first generations of stars, called population 3 stars, were behemoths made almost purely of hydrogen and helium. They lived fast, burned hot, and died young in colossal supernova. It was only through these violent deaths that they forged and scattered the heavier elements like carbon, nitrogen, oxygen, and iron into the cosmic forge. These are the essential building blocks of planets, oceans, and life itself. It took multiple generations of stellar life and death, over billions of years, to enrich the galactic gas clouds with enough of these precious elements. Our solar system and our planet are the beneficiaries of this long, slow process. We are latecomers born from the ashes of countless ancient stars. If the universe needed most of its lifetime to become chemically mature enough for Earth-like planets, then perhaps most technological civilizations are also late bloomers, appearing only recently in cosmic terms. We might simply be among the first to arrive at the party, but timing is only one piece of the puzzle. The universe's physical laws and constants appear fine-tuned in a way that allows for complexity. If the strength of gravity were slightly stronger, stars would burn out too quickly. If the nuclear force were slightly weaker, hydrogen would not fuse and stars would never shine. This delicate balance suggests that habitable pockets like ours might be extraordinarily rare jewels in a vast, barren cosmos. The conditions that allowed a stable planet, a protective moon, and a magnetic field to arise around a quiet, long-lived star like our Sun could be a cosmic lottery with near impossible odds. Furthermore, the universe itself may be actively hostile to the development and survival of advanced civilizations. Galactic centers are bathed in lethal radiation from supermassive black holes. Stars in dense clusters can have their planetary systems violently disrupted by close encounters. And even on a stable planet, countless filters, from asteroid impacts to self-inflicted catastrophes, could halt a civilization's progress long before it learns to signal the stars. So the great silence we hear may not be empty. It may be the sound of a young universe still preparing its stage, of a cosmic recipe where the ingredients for intelligence are exceedingly scarce, or of a relentless series of challenges that few, if any, survive. We are either tragically alone, precociously early, or listening for a signal we do not yet know how to hear. That profound cosmic silence forces us to confront another deep mystery, one written into the very first light we see. The cosmic microwave background, that baby picture of the universe, presents a problem so severe it nearly broke the Big Bang theory. This is the horizon problem, and it is our 10th forgotten fact. Look up at the night sky in two completely opposite directions. The regions of space you are looking at are separated by over 28 billion light years. Since the universe is only 13.8 billion years old, light, and therefore any influence, has not had enough time to travel from one of those regions to the other. They are forever beyond each other's cosmic horizon, eternally out of touch. Yet, when we measure the temperature of the cosmic microwave background coming from these opposite sides of the sky, they are identical to an astonishing precision, down to 1 part in 100,000. How can two parts of the universe that have never exchanged a single photon, never communicated in any way, know to be exactly the same temperature? It is as if you placed 2 cups of coffee in separate, soundproof rooms on opposite sides of the planet, and without any contact, they both cool to precisely 74.3 degrees Fahrenheit. This perfect thermal equilibrium defies common sense. In the standard Big Bang model without inflation, there simply was not enough time for heat to flow and even out the temperature across such vast, disconnected distances. The early universe should be a patchwork of hot and cold zones, not this stunningly uniform blanket. This was a glaring flaw, a crack in the foundation. The solution arrived with the theory of cosmic inflation. Imagine the observable universe before inflation, not as a vast expanse, but as a subatomic speck. This tiny region was so small that all parts of it were in intimate contact, easily exchanging energy and reaching a uniform temperature. Then, in an instant, inflation acted like a cosmic magnifying glass of unimaginable power. That tiny, thermally connected speck was stretched exponentially, faster than light, to become a volume larger than our entire observable universe today. The two opposite points on our sky that now seem forever separated were once neighbors, practically touching within that original ultra-hot dot. Inflation did not allow them to communicate. It preserved the communication they had already achieved. It took a state of local harmony and stretched it across the entire cosmos, solving the horizon problem with breathtaking elegance. The perfect uniformity we see is not a mysterious coincidence. It is the fossilized imprint of a universe that was once small enough to whisper to all of itself. Inflation's stretch gave us a uniform cosmos, but what came next was a darkness deeper than any night. For nearly 400,000 years after the Big Bang, the universe was not a place of stars and galaxies. It was an impenetrable, glowing fog. This is the era of recombination, our 11th forgotten fact, and it marks the moment the universe finally became transparent, releasing its very first light. Picture the cosmos in its first few hundred millennia, a seething, opaque plasma. Temperatures were still so incredibly high that electrons could not bind to atomic nuclei. Protons and electrons zipped around freely, constantly scattering the intense radiation that filled every corner. Photons, the particles of light, could not travel more than a tiny fraction of an inch before crashing into a free electron, bouncing off in a new direction. The universe was a blinding, chaotic prison of light, trapped within its own superheated matter. Then, as expansion continued its relentless work, the temperature finally dropped below a critical threshold around 3000 Kelvin. This is cool enough for the frantic electrons to be captured by protons, forming the first stable atoms of neutral hydrogen. In an instant, the free electrons that had been scattering light for eons were gone, locked into atomic orbits. The fog lifted. The photons, which had been trapped in a constant pinball game for hundreds of thousands of years, were suddenly set free. They could now stream across the cosmos in straight lines, unimpeded. That moment of liberation, the clearing of the cosmic fog, is what we call recombination, and the light released in that instant is the oldest thing we can possibly see. We detect it today not as visible light but as microwave radiation. The universe has expanded by a factor of over 1,000 since that day, stretching those once visible photons into longer, cooler wavelengths. This is the cosmic microwave background, a ghostly afterglow bathing the entire universe. It is not a picture of the Big Bang itself, but a baby picture of the universe at the tender age of 380,000 years. Every direction we look, we are seeing the glowing surface of that primordial fog bank as it thinned and vanished. The subtle variations in its temperature, those hot and cold spots we map so carefully, are the imprints of the denser regions where gravity would eventually get to work, pulling matter together over billions of years to form galaxies and stars. So the first light of creation was not a brilliant star twinkling in the void. It was the soft, uniform glow of a newborn universe taking its first clear breath, a fossilized flash that has been traveling for over 13 billion years to reach our eyes, telling us the story of when everything became visible. That first light shows us a universe of stunning uniformity, but look closer. The cosmic microwave background is not perfectly smooth. It is a tapestry of subtle hot and cold spots, temperature variations of just a few millionths of a degree. These faint imperfections are the most important fingerprints in all of cosmology, for they are the origin of everything. They are the fossilized imprints of quantum fluctuations, microscopic ripples born in the universe's first fleeting instant, stretched to cosmic proportions. This is the forgotten fact that connects the smallest rules of reality to the grandest structures we see. In the furious expansion of inflation, space itself was not a passive stage. At the quantum level, even a perfect vacuum is not truly empty. It is a seething, bubbling foam where pairs of virtual particles constantly wink in and out of existence, borrowing energy from the universe for a fleeting moment before annihilating. This quantum jitter creates tiny, random fluctuations in energy density. In the normal world, these fluctuations are immeasurably small and vanish almost instantly. But during inflation, something miraculous happened. The universe expanded faster than light. A quantum fluctuation that appeared in one location did not have time to disappear before space itself stretched, locking that microscopic ripple into the fabric of reality and magnifying it to a size larger than a galaxy. Imagine a tiny, nearly invisible wrinkle on the surface of a deflated balloon. As you blow the balloon up to the size of a planet, that wrinkle becomes a vast continent-sized ridge. Inflation did exactly this to the quantum foam of the infant cosmos. These stretched ripples were not in matter, but in the very energy field driving inflation. As that field decayed and transformed into the hot soup of particles, the ripples became slight differences in density, tiny pockets where the early universe was ever so slightly denser or thinner than average. Gravity, the great architect, then went to work on this blueprint. over hundreds of millions of years, gravity patiently pulled matter toward those slightly denser regions. Atoms of hydrogen and helium, along with the invisible scaffolding of dark matter, began to slowly accumulate. The denser spots grew denser, their gravitational pull strengthening, drawing in even more material from the surrounding thinner areas. What began as a quantum whisper became a gravitational shout. The largest of these density seeds eventually collapsed under their own weight to form the first stars and the cores of the first galaxies. Smaller seeds became globular clusters or were swallowed by larger neighbors, and the vast, underdense regions, the cosmic valleys, became the great voids we see today, immense empty spaces spanning hundreds of millions of light years. The entire cosmic web, that magnificent, lace-like structure of galaxy clusters and filaments surrounding immense voids, is a direct, scaled-up map of those initial quantum jitters. Every galaxy, every star, every planet, and every one of us originated from a random quantum fluctuation in the first trillionth of a second of time. Our existence is rooted in a fundamental uncertainty, a cosmic dice roll at the very beginning of everything. The quantum seeds of our existence present a profound puzzle, but an even deeper one lies in the simple fact that we exist at all. According to everything we know about particle physics, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every proton born, an antiproton should have been its twin. For every electron, a positron. And when these matter and antimatter particles meet, they annihilate in a flash of pure energy, leaving nothing behind. If the universe had begun with perfect symmetry, all of its particles should have mutually destroyed one another in the first second, leaving a cosmos filled with nothing but a dull, eternal glow of radiation. There would be no atoms, no stars, no planets, and certainly no one to wonder about it. Yet here we are. The undeniable reality is that our universe is made almost entirely of matter. Somewhere in the earliest moments, a critical imbalance was introduced. One extra particle of matter survived for every billion matter-antimatter pairs that annihilated. That one in a billion surplus is everything. Every galaxy, every rock, every living thing is made from that tiny, inexplicable excess. This is the mystery of baryon asymmetry, and solving it requires a process called baryogenesis. Scientists believe three specific conditions had to be met in the early universe to create our matter-dominated reality. First, there needed to be a violation of something called CP symmetry. In simple terms, CP symmetry means that the laws of physics should treat particles and their mirror image antiparticles the same way. If this symmetry were perfect, matter and antimatter would behave identically, and no net matter could ever emerge. We know CP violation exists because we have observed it in certain rare particle decays here on Earth. But the amount we have seen is far, far too small to account for the vast amount of matter in the cosmos. The early universe must have hosted a much more powerful source of CP violation, a fundamental lopsidedness in the laws of nature that favored the production of matter over antimatter. The second condition is baryon number violation. Baryons are particles like protons and neutrons, the heavy building blocks of atoms. In our everyday world, baryon number is conserved, meaning you cannot just create or destroy a proton out of nothing. But to generate an excess of matter from an initially neutral state, the early universe must have temporarily broken this rule. Some ultra-high-energy process must have allowed for reactions that produced more baryons than antibaryons. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces, predict such events could have occurred when the universe was unimaginably hot and dense. The third and final condition is that all of this had to happen out of thermal equilibrium. If the universe were in a perfect, smooth, balanced state, any matter excess created would just get wiped out again by reverse reactions. The process needed a one-way street, a moment of cosmic upheaval where conditions changed so rapidly that the newly created matter asymmetry could be frozen in place before nature could correct it. The rapid expansion of the universe during its inflationary phase or during later phase transitions could have provided exactly this kind of departure from equilibrium. The frustrating truth is that while we have identified these three necessary ingredients, we have not found a complete recipe that fits all our observations. The known CP violation is too weak, and we have no direct evidence for baryon number violation at the required scale. This means our standard model of particle physics is incomplete. The answer lies somewhere beyond it, in physics we have not yet discovered. Experiments like giant particle colliders are searching for clues, and observations of the cosmic microwave background might hold subtle hints. The origin of matter, the very stuff of our being, remains one of the greatest unsolved problems in all of science, a quiet reminder that our existence hinges on a broken symmetry we do not yet understand. That 1 in a billion surplus of matter is the ultimate reason we are here, but the evidence for our violent origin is painted across the entire sky. The cosmic microwave background is more than just ancient light, it is a nearly perfect fossil. Its spectrum matches that of a theoretical object called a blackbody with a precision that is almost unnerving. A blackbody is an idealized object that absorbs all radiation that hits it and then re-emits it with a very specific signature, a unique fingerprint of intensity at every wavelength that depends only on its temperature. Think of a piece of iron heating in a forge. As it gets hotter, it glows red, then orange, then white. The color and intensity of that glow follow a precise blackbody curve dictated by the iron's temperature. The universe at the tender age of 380,000 years was a single, vast, glowing object at a temperature of about 3,000 Kelvin. It should have emitted a perfect blackbody spectrum. For decades, this was a key prediction of the Big Bang theory, but it was incredibly difficult to measure from Earth's surface, where our atmosphere blocks most of these microwaves. The proof required going to space. The Cosmic Background Explorer satellite, or COBE, launched in 1989, was designed to do just that. Its instruments scanned the sky, and the data it sent back caused a sensation. The curve it measured was a flawless match to a blackbody at 2.725 Kelvin, the cooled remnant of that ancient glow. The fit was so perfect that when scientists presented the graph at an astronomy meeting, the audience broke into spontaneous applause. One cosmologist famously called it the discovery of the century, if not all time. It was the smoking gun for the Big Bang. Later missions, the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, measured this blackbody spectrum with even more breathtaking precision. Planck's data showed the agreement is exact to better than 1 part in 10,000. This is not just close, it is a bullseye. This incredible match is why we call the cosmic microwave background the universe's baby picture. It is not an artist's impression or a theoretical sketch. It is a direct, precise measurement of the universe's state at a specific moment in its infancy. That perfect blackbody curve tells us the early universe was in a state of near-perfect thermal equilibrium, a hot, dense, and remarkably simple soup. Every tiny deviation from that perfection, every minuscule ripple in the temperature, then becomes the crucial clue, the blueprint from which our complex cosmos was built. That perfect blackbody glow faded into a darkness deeper than any we can comprehend. For hundreds of millions of years, the universe entered a profound and silent chapter known as the Cosmic Dark Ages. This was not a metaphor, it was a literal reality. After the brilliant flash of recombination cleared the fog, the cosmos was left in utter blackness. No stars twinkled, no galaxies swirled. The only light was the faint, cooling afterglow of the Big Bang itself, stretched into invisible microwaves. The universe was a vast, featureless expanse of neutral hydrogen and helium gas. slowly cooling and drifting through the expanding void, shepherded by the invisible gravitational wells of dark matter. It was a place of perfect stillness and profound cold, a canvas waiting for its first brushstroke of light. This era is a true dark age in a historical sense because we have almost no direct observations of it. It is a cosmic blind spot, a gap in our timeline between the baby picture of the cosmic microwave background and the first glimmers of starlight we can detect from the earliest galaxies. We are left to piece together this epoch through theory and the faintest of clues. Within that immense darkness, gravity was the only artist at work. Those tiny density ripples imprinted from the quantum dawn provided the only structure. Over achingly long eons, the slightly denser patches of dark matter began to pull in more dark matter, and with it, the ordinary hydrogen gas. These were the seeds of the first protogalaxies, vast, amorphous clouds slowly collapsing under their own weight. As they contracted, the gas within them began to heat up. But for a very long time, it was not enough to ignite nuclear fusion. The universe simply waited, cooling and darkening further. The end of this cosmic night was not a sudden sunrise, but a gradual, patchy awakening. Deep within the hearts of the densest gas clouds, conditions finally became extreme enough. Temperatures soared to millions of degrees, and pressure overcame the repulsive force between hydrogen nuclei. In a flash of energy that had not been seen since the first minutes of the Big Bang, nuclear fusion ignited. The first stars were born. Astronomers called them population 3 stars, and they were unlike anything in our modern universe. Made from the pristine, pure hydrogen and helium forged in the Big Bang, with no heavier elements to help them cool and fragment, these stars were monsters. They likely formed in isolation or small groups within those protogalactic clouds, and they were behemoths hundreds of times more massive than our Sun. Such mass came with a ferocious appetite for fuel. They burned at searing temperatures, shining with a blistering blue-white light that was intensely rich in ultraviolet radiation. This was the cosmic dawn. The first starlight in over 100 million years began to pierce the universal dark. But these stars did not just bring light, they brought transformation. Their powerful ultraviolet photons began to rip electrons away from the surrounding neutral hydrogen atoms, a process called reionization. Slowly, patch by patch, the universe's hydrogen was being reionized, turned back into a plasma. This time, however, the plasma was not a uniform fog, but a web of ionized bubbles surrounding the first stars and galaxies, like bright clearings in a dark forest. The population 3 stars lived fast and died young, exploding in spectacular supernova within just a few million years. Their violent deaths were just as important as their births. In their cataclysmic final moments, these first stars forged the first heavy elements carbon, oxygen, silicon, iron, and blasted them out into the primordial gas. This cosmic pollution was the gift that made everything after possible. It seeded the clouds for the next generation of smaller, longer-lived stars and eventually for rocky planets and the chemistry of life. The Dark Ages were over, not with a whimper, but with the brilliant, explosive birth and death of the universe's first magnificent giants. Those first monstrous stars were cosmic titans of a purity we will never see again. They are classified as population 3 stars, the third and earliest generation in our stellar family tree. Unlike the stars of today, which formed from gas enriched by previous stellar generations, these pioneers were born from the pristine, primordial material left over from the Big Bang itself. This was a universe of just hydrogen, helium, and a whisper of lithium. That chemical simplicity had a profound consequence. In modern star-forming clouds, elements like carbon and oxygen act as a coolant, allowing the gas to fragment into many smaller clumps. Without these heavy elements, the primordial clouds could not cool efficiently. They collapsed into far fewer, far more massive objects. The result was not a sparkling cluster of sun-like stars, but the birth of isolated behemoths. Current models suggest a typical population 3-star could have been between 100 and 1,000 times the mass of our Sun. Picture a star so vast that if placed at the center of our solar system, its surface might extend beyond the orbit of Jupiter. These stars did not just dwarf our Sun in size, they utterly eclipsed it in ferocity. Their immense mass created crushing pressures and temperatures at their cores, driving nuclear fusion at a frantic, desperate rate. They burned through their vast reserves of hydrogen fuel in just a few million years, a cosmic blink compared to the 10-billion-year lifespan of our own Sun. Their light was not the gentle yellow-white we know, but an intense, searing blue-white, flooding the early cosmos with torrents of ultraviolet radiation. This harsh light was the sculptor of the early universe, beginning the great work of reionization, stripping electrons from atoms and clearing the fog for future generations. But their death was even more transformative than their brilliant life. A star of such staggering mass does not fade quietly. When its core finally ran out of fuel, it could no longer support its own immense weight. It collapsed catastrophically in a supernova explosion of almost unimaginable power, known as a pair instability supernova. In this event, conditions become so extreme that gamma-ray photons in the core spontaneously create pairs of electrons and positrons. This sudden removal of radiation pressure causes the core to collapse further in a runaway chain reaction, leading to a thermonuclear detonation so complete that it obliterates the entire star, leaving behind no black hole or neutron star, just scattered stardust. In that final, universe-shaking blast, the alchemy of creation reached a new peak. The furnace of its life and the inferno of its death fused hydrogen and helium into the first heavy elements. Carbon, oxygen, nitrogen, silicon, and iron were forged in that instant and blasted out into the surrounding void at nearly the speed of light. This was the universe's first act of serious chemical enrichment. Those newly minted atoms, this cosmic soot, polluted the pristine gas clouds of the early cosmos. It was a gift of profound consequence. When the next generation of stars formed, they did so from this slightly enriched material. Those cooling elements allowed the gas to fragment more easily, leading to stars of more moderate sizes like our Sun with much longer lifespans. And around those stable, long-lived stars, the heavier elements could clump together to form asteroids, comets, rocky planets, and ultimately, the complex chemistry that leads to life. Every atom of iron in your blood, every atom of calcium in your bones, and every atom of oxygen you breathe was forged in the heart of a star that died long before our Sun was born. But the very first of those elements, the ones that started the entire chain, came from those magnificent, terrifying monsters of the cosmic dawn. The brilliant, violent deaths of those first stars set the stage for everything to come, but they could not predict the ultimate fate of the cosmos they helped create. For most of the 20th century, cosmologists believed they understood that fate. The story seemed straightforward, a grand cosmic tug-of-war. After the initial fireball of the Big Bang, the universe was expanding, throwing galaxies apart. But gravity, the relentless pull of all the matter in the cosmos, was constantly working against that expansion, like a brake slowly being applied. The central question was, how strong was that brake? Would gravity eventually halt the expansion and pull everything back together in a fiery big crunch? Or would the universe have just enough energy to keep expanding forever, coasting toward a cold, dark, but gradual end? In the 1990s, two independent teams of astronomers set out to measure the universe's deceleration with unprecedented precision. Their tool was a specific kind of stellar explosion, a Type Ia supernova. These occur in binary star systems where a dense white dwarf star steals matter from its companion. Once the white dwarf reaches a critical mass, about 1.4 times the mass of our Sun, it undergoes a runaway thermonuclear explosion. Because this critical mass is always the same, the intrinsic brightness of these supernovae is remarkably consistent. They are what astronomers call standard candles, cosmic mile markers. By measuring how bright such a supernova appears from Earth, you can calculate its distance, and by analyzing the redshift of its light, you can determine how much the universe has stretched since the explosion occurred. Comparing supernova at different distances allows you to map how the expansion rate has changed over cosmic history. The teams, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, painstakingly searched for these rare explosions in galaxies billions of light-years away. They expected to see that the more distant supernova, which exploded when the universe was younger, showed signs of a faster expansion rate back then, proving that the expansion was indeed slowing down over time. The data came in, and the results were not just surprising, they were universe-shattering. The distant supernova were fainter than they should have been. This meant they were farther away than the standard model predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was pushing galaxies apart with ever-increasing strength, overcoming the collective gravity of all the cosmos. The announcement in 1998 sent shockwaves through the scientific community. It was a discovery so profound it earned the researchers the Nobel Prize in Physics in 2011. This accelerating expansion forced a radical rewrite of cosmic destiny. The universe's fate was no longer a slow fade or a dramatic collapse, but a cold, lonely, and runaway drift into infinite separation. Galaxies not already bound by gravity would eventually be pushed so far apart that their light could never reach us. The cosmic web would be torn apart, leaving islands of star systems isolated in an ever-darkening, ever-expanding void. To explain this shocking behavior, cosmologists resurrected an old idea from Einstein's equations, a cosmological constant, and gave it a new name, dark energy. It is not a substance we can touch or see, but rather a property of empty space itself. As the universe expands, more space is created, and with it, more of this repulsive energy, leading to a feedback loop of acceleration. Today, dark energy constitutes about 68% of the total energy budget of the universe. It is the dominant force shaping our cosmic future, and we have almost no idea what it truly is. Is it a constant energy woven into the fabric of space-time, or a dynamic field that could change over time? The answer will determine whether the universe ends in a quiet freeze or something even more strange. This forgotten fact, discovered in the faint light of dying stars, tells us that the most powerful force in the cosmos is one we cannot see, a ghost in the machine that is actively writing an ending we are only beginning to read. Dark energy's acceleration may be the final chapter for our universe, but it could be the opening sentence for an infinity of others. This brings us to a truly mind-bending forgotten fact: the possibility that our entire cosmos is just one bubble in a frothing, endless sea of other universes. This is the multiverse, and while it sounds like pure science fiction, it emerges as a surprisingly plausible consequence of the same theory that solved our earlier puzzles: cosmic inflation. The standard story of inflation describes a single, brief burst of exponential expansion that smoothed and stretched our observable universe. But what if that process never truly stopped? The theory of eternal inflation suggests that once inflation begins in some region of space-time, it can become self-perpetuating, a runaway process that creates new inflating regions faster than it can ever be completely shut off. Imagine a pot of water beginning to boil. A single bubble forms at the bottom and rises. In our universe, that bubble popped, ending inflation and creating our hot Big Bang. But in eternal inflation, the boiling never ceases. The pot is infinite, and new bubbles are constantly nucleating out of the still inflating background, each one a separate universe with its own Big Bang. Our entire cosmos, with all its hundreds of billions of galaxies, is just one of those bubbles, This is not a metaphor, it is a direct mathematical outcome of the equations governing the inflattened field, the energy that drove the expansion. In this picture, the multiverse is not a choice, it is an inevitable byproduct. The staggering implication is that each of these bubble universes could be a separate reality with its own unique set of physical laws and constants. When a bubble nucleates and inflation ends inside it, the inflattened field decays, releasing its energy. But the way it decays, a process called symmetry breaking, is random. Think of a ball rolling down a rugged, mountainous landscape with countless valleys. The valley it finally settles into determines the local landscape, the effective laws of physics for that bubble. In one bubble, it might settle into a valley where the strength of gravity is strong, leading to a universe that collapses almost instantly. In another, it might settle where the nuclear force is weak, preventing atoms from ever forming. Our universe settled into a very specific, remarkably narrow valley where the constants allow for stars, planets, and life. In an eternally inflating multiverse, every possible set of constants, every conceivable physical reality, would be realized somewhere in the infinite froth. We do not live in a special universe, we simply live in one of the rare bubbles where conditions allowed observers like us to arise and ask the question. This idea, known as the anthropic principle, shifts the perspective on our fine-tuned existence. It is not that the universe was designed for life, but that life can only exist in the universes capable of producing it. While we cannot see these other bubbles as they are forever beyond our cosmic horizon, the mathematics suggests they are a natural, perhaps unavoidable, consequence of our best theory of the beginning. The multiverse remains speculative, a frontier of cosmology rather than established fact. Yet it stands as a profound reminder that our origin story may be far grander and stranger than a single explosion in an empty void. We might be just one page in an infinite library of realities, a single note in a cosmic symphony whose full scale we may never comprehend. The multiverse may be an unseeable sea of possibilities, but a far more tangible ghost from the dawn of time is flowing through you right now. Billions of these particles pass through every square centimeter of your body and the entire Earth every single second without a trace. This is the cosmic neutrino background, and it is the universe's second oldest fossil. While the cosmic microwave background shows us the universe at 380,000 years old, this neutrino sea offers a snapshot from a mere 1 second after the Big Bang. To understand why, we need to rewind to that first frantic second. In the earliest, hottest moments, the universe was so dense that even neutrinos, famously ghostly particles that barely interact with anything, were trapped. They bounced and scattered in the thick plasma, locked in constant interaction. Then, roughly 1 second after the beginning, the universe had expanded and cooled just enough. Suddenly, neutrinos could travel freely. They decoupled from matter, streaming out into the expanding cosmos, never to be significantly disturbed again. This moment, neutrino decoupling, created a permanent background radiation field, just like the photon decoupling that gave us the CMB, but from an epoch over 300,000 times earlier. This background is not made of light. It is a vast, diffuse ocean of the lowest energy neutrinos imaginable, permeating all of space. Detecting it, however, is a monumental challenge. Neutrinos live up to their ghostly nickname. They have no electric charge and almost no mass, allowing them to pass through entire planets with only the rarest chance of a collision. The neutrinos we detect from the Sun or from supernova are high energy and relatively recent. The cosmic neutrino background particles, in contrast, have been cooled by the expansion of the universe for 13.8 billion years. They are now incredibly sluggish, with energies so low that they are effectively frozen. Catching one is like trying to detect the gentle heat of a candle flame on the other side of a mountain during a hurricane. Our current detectors, built deep underground to shield from cosmic rays, are tuned for higher energy events. They are utterly blind to these primordial whispers. Yet the scientific payoff for a detection would be immeasurable. Observing the CNB would be like opening a time capsule from the universe's first heartbeat. It would give us a direct measurement of conditions just 1 second after the Big Bang, allowing us to test our models of particle physics under the most extreme energies. It could tell us about the total number of neutrino species, constrain their tiny masses with unprecedented precision, and reveal details about the violent processes that shaped the universe long before the first atoms ever formed. Some proposed methods for this ultimate detection involve looking for an almost impossibly rare interaction, where one of these ancient, low-energy neutrinos scatters off an atomic nucleus and gives it a minuscule kick. Others involve searching for subtle imprints the neutrino background left on the formation of the very first large-scale structures in the universe. Finding this ghostly sea would be a triumph of human ingenuity, allowing us to see past the brilliant flash of recombination and peer into the universe's fiery, formative instant. Our universe is not a still and placid sea, but a river in motion, and we are caught in a current we cannot see. Every galaxy, including our own Milky Way, is not simply drifting apart in the grand expansion. It is also being pulled by the silent, cumulative gravity of everything around it. We are sailing on a hidden tide, and at the end of that tide lies one of the greatest cosmic mysteries of our local universe, the Great Attractor. This is not a single object like a star or a black hole. It is a colossal gravitational anomaly, a focal point in intergalactic space with the mass of tens of thousands of galaxies, pulling our entire galactic neighborhood toward it at over 2 million kilometers per hour. For decades, its true nature was hidden from us, lying in the zone of avoidance, a region of the sky obscured by the dense gas and dust of our own galaxy's central plane. It was like trying to study a distant city while standing in a thick fog. We knew something massive was there because of its gravitational influence. By meticulously mapping the motions of thousands of galaxies, astronomers saw a vast river of galaxies, including our own and the entire local group, all streaming in the same direction toward the constellations of Centaurus and Hydra. This coherent motion on such an immense scale could only mean one thing: an enormous concentration of mass was tugging on us. The Great Attractor is the gravitational heart of what we call the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our home supercluster, a web of over 100,000 galaxies spanning 500 million light-years. The Great Attractor sits at its dense core, a gravitational basin where the cosmic flows of galaxies converge. But here is the crucial connection to our origins. This immense structure is not a random accident. It is a direct descendant of those primordial quantum fluctuations from the universe's first instant. Billions of years ago, that specific patch of the early cosmos was ever so slightly denser than its surroundings. Over eons, gravity amplified that tiny advantage. It drew in dark matter, then gas, then galaxies, growing into the titanic knot of mass we now sense pulling us onward. The Great Attractor is a living fossil, a testament to how the microscopic blueprint of inflation was etched into the large-scale architecture of the cosmos. Our motion toward it is not a local curiosity. It is our participation in a dance choreographed at the dawn of time, a river of galaxies flowing down a slope that was carved in the first trillionth of a second of existence. That hidden current flowing toward the Great Attractor travels across a stage of immense and surprising simplicity. The grand geometry of our universe, the very shape of space on the largest scales, is not curved like a sphere or twisted like a saddle. It is flat. This is not a metaphor about maps or planets, but a precise statement about the rules of geometry that govern the cosmos. In a flat universe, the classic rules we learned in school, Euclid's geometry, hold true. Parallel lines never meet. The angles of a triangle always add up to 180 degrees, and the shortest distance between 2 points is a straight line. We have confirmed this flatness by reading the most ancient text we have, the cosmic microwave background. The subtle patterns of hot and cold spots in that afterglow act like cosmic rulers. Scientists can measure the apparent size of these spots on the sky. In a universe with positive curvature, like the surface of a sphere, parallel light rays would converge. Distant spots would appear larger than they truly are. In a universe with negative curvature, like a saddle, light rays would diverge, making distant spots appear smaller. The exquisite measurements from satellites like WMAP and Planck show the spots appear exactly the size predicted for a perfectly flat geometry. The data leaves almost no room for doubt. This flatness is a direct echo from the universe's explosive infancy. For space to be flat today, 13.8 billion years after the Big Bang, its density at the very beginning had to be exquisitely fine-tuned to a critical value. Think of it as a cosmic balancing act. Two immense forces have been wrestling since the beginning: the outward momentum of the Big Bang's expansion and the inward pull of all gravity from all matter and energy. If the density of the universe were too high, gravity would win. Space would curve back on itself like a sphere, eventually collapsing in a big crunch. If the density were too low, expansion would win completely, leading to a hyperbolic, saddle-shaped curvature and a universe that flies apart into infinite thinness. The fact that we measure flatness means the density is precisely at the critical value, the knife edge between these two fates. The initial conditions had to be balanced to an accuracy of 1 part in 10 to the power of 60, a number so incomprehensibly precise it is like balancing a pencil on its tip for billions of years. Such perfection seems wildly improbable, a cosmic coincidence of staggering proportions. This is where inflation provides its elegant solution. That furious exponential stretch in the first instant would have smoothed out any initial curvature, flattening the universe like inflating a wrinkled balloon. No matter how curved or crumpled a tiny patch of the early universe was, inflating it to the size of our observable cosmos would make it appear perfectly flat to any observer inside, just as a small patch on the surface of an enormous balloon feels flat to an ant. The flatness we measure is not a lucky accident, but a predicted consequence of that primordial growth spurt. It tells us that the total energy density of the cosmos, including ordinary matter, and dark energy, adds up to that perfect critical balance. Our geometry is a permanent record of a moment when everything was stretched smooth. That flat geometry provides the perfect stage for our most powerful time machine. We have spoken of the cosmic microwave background as a baby picture, but its true nature is even more specific and wondrous. It is a fossilized flash from a single spherical shell in space, a moment frozen in time called the last scattering surface. When we point our telescopes to map this ancient glow, we are not looking at a distant object like a star. We are looking at a wall. This wall is not made of brick or stone, but of a fog of hydrogen atoms that existed everywhere all at once, exactly 380,000 years after the Big Bang. At that precise moment, the universe cooled enough for electrons to combine with protons, forming neutral atoms and suddenly clearing the cosmic fog. The photons that had been trapped, bouncing around for eons, were finally set free. They began streaming across the universe in every direction. The place where that happened, for every point in space, is the last scattering surface. It is the final moment those photons scattered off matter before beginning their 13.8 billion year journey to our detectors. Think of it like being inside a giant spherical cloud. The cloud is filled with a dense, glowing mist. Suddenly, from the center to the edge, the mist clears instantaneously. The light from every point inside that cloud now races outward. If you were standing at the center, you would first see light from the particles right next to you, then light from particles farther and farther away, each showing you what that part of the cloud looked like at the exact moment of clearing. We are not at the center of the universe, but due to the expansion of space, we experience the same effect. the last scattering surface surrounds us in all directions. Its distance is staggering because the universe has expanded enormously since that light was emitted. The location of that ancient fog bank is now about 46 billion light-years away from us in every direction. This means we are looking at light that has traveled for 13.8 billion years, but the source of that light has been carried away by the stretching of space to a position nearly 4 times farther. When we look at the microwave sky, we are peering through a telescope that looks not just across space, but directly back in time, to a specific date in cosmic history. We see the universe not as an infant, but as a toddler taking its first clear breath. The subtle patterns in that light, those hot and cold spots, are a snapshot of the density variations at that exact epoch. They are the raw material, the primordial blueprint from which everything we see today would eventually form. This spherical shell is our ultimate observational anchor, a firm date we can point to in the cosmic calendar. It provides a direct observational window into conditions long before any star or galaxy existed, offering irrefutable evidence for the hot, dense, and remarkably simple state of the early cosmos. Every microwave photon that hits a telescope is a messenger from that single, transformative moment, carrying a story that began before time itself had any real meaning. The last scattering surface captured a universe of simple atoms, but chemistry, the dance of molecules, was about to begin. This leads us to a forgotten fact of profound simplicity. The very first molecular bond in the cosmos was not water, not carbon dioxide, but a fragile, exotic ion called helium hydride. Long before the first stars forged heavier elements, the universe was a vast, cooling expanse of hydrogen and helium nuclei and free electrons. As the temperature continued to drop after recombination, a new window opened. Helium atoms, having 2 protons and 2 electrons, are notoriously inert and reluctant to bond with anything. But in the cooling plasma, a rare opportunity arose. Occasionally, a helium atom would collide with a lone proton, a hydrogen nucleus. In the right collision, the helium atom could briefly share its electrons, forming a temporary, unstable union, the helium hydride ion. This molecule, He+, is incredibly fragile. Even a slight bump from another particle or a photon of the right energy could tear it apart. For it to survive, the universe needed to be in a very specific Goldilocks zone, cool enough for atoms to exist but still warm enough to provide a sparse population of free protons, and with radiation that was not so harsh it would immediately destroy the bond. This delicate dance occurred when the universe was roughly 100 million years old during the late Dark Ages. The significance of this first, trembling handshake between atoms cannot be overstated. It was the proof of concept for molecular chemistry in the cosmos. The formation of helium hydride initiated a cascade. Once it existed, it could interact with the abundant neutral hydrogen atoms. In a series of reactions, the helium hydride ion would donate its proton to a hydrogen atom, creating a molecule of molecular hydrogen, 2 hydrogen atoms bound together, H2. Molecular hydrogen is the universe's primary coolant. Unlike single atoms, molecules can rotate and vibrate, and when they collide, they can radiate away heat. This ability to cool is the critical trigger for star formation. Without molecular hydrogen, the vast clouds of gas collapsing under gravity could not shed their heat. They would simply bounce back, unable to condense into the dense cores needed to ignite nuclear fusion. The fragile helium hydride ion was the essential first step, the spark that lit the fuse for the chemistry of cooling. It transformed the universe from a monotone sea of atoms into a place where complex structures could begin to chill and collapse. Every star that ever shone, every stellar nursery that gave birth to planets, owes its existence to that first, tentative bond between a reluctant helium atom and a lonely proton. The entire epic of cosmic chemistry, which would later, in the hearts of stars and the nebulae of their deaths, forged the carbon in our cells and the oxygen in our lungs, began with this single, ghostly molecule in the dark. The chemistry that built our world operates within a universe whose ultimate fate is controlled by a ghost. Dark energy's dominance is not just a mystery of what it is, but of when it arose. This leads us to a profound and unsettling coincidence, one that whispers of either incredible luck or a fundamental gap in our understanding. For most of cosmic history, the universe was dominated by matter and radiation. Gravity reigned, slowing the expansion and sculpting galaxies. Dark energy, if it existed at all, was an utterly negligible whisper in the background. But as the universe expanded and matter thinned out, its gravitational grip weakened. At some point, the repulsive push of dark energy, which seems to be a property of space itself, finally matched and then overwhelmed the pull of gravity. The extraordinary fact is that this cosmic crossover, this moment when dark energy became the dominant force, happened in what we consider the present epoch. The density of dark energy today is curiously, almost suspiciously, comparable to the average density of matter in the universe right now. They are within an order of magnitude of each other. Why now? From a cosmic perspective, this is an astonishing coincidence. The universe is 13.8 billion years old. Dark energy could have become dominant when the universe was a fraction of a second old, or trillions of years in the future. Instead, it took over roughly when complex life emerged on at least one planet to notice it. This temporal fine-tuning makes theorists deeply uncomfortable. In science, a coincidence of this magnitude often points to a missing piece of the puzzle. One compelling possibility is that dark energy is not a constant but something that evolves. Perhaps it is a dynamic field like the inflattened field of the early universe, but far weaker and slower changing. This idea, called quintessence, suggests dark energy's density could have been different in the past and may change again in the future. In such a model, the fact that it matches matter density today might not be a bizarre accident, but a temporary phase in a long, slow cosmic cycle. Another, more radical thought is that this coincidence is an observational selection effect. The anthropic principle suggests that we can only exist in a universe where the conditions allow for observers. If dark energy were much stronger, it would have accelerated expansion so quickly that galaxies and stars could never have formed. We simply would not be here to wonder about it. Our presence selects for a universe where dark energy's rise to power happens late enough for structures like us to arise. Whether the answer lies in a new physics of evolving fields or in the stark logic of cosmic selection, the coincidence problem remains a glaring clue. It tells us that the story of dark energy is inextricably linked to the story of our own existence, and that the universe's final chapter may have been written into its first. The coincidence of our existence alongside dark energies rise points to a future we can predict but will never witness. Our 25th forgotten fact forces us to look not to the beginning, but to the ultimate end of the cosmic story we have been tracing. Based on the strange dominance of dark energy, scientists see two possible destinies for our universe, one of a slow, cold fade and another of a violent, final shredding. The first and long-standing prediction is known as the heat death or the Big Freeze. This is the triumph of entropy, the universal trend toward disorder. Imagine a clock slowly winding down. Trillions of years from now, the last stars will exhaust their fuel and burn out. Galaxies will grow dark. Black holes will themselves evaporate over unimaginable eons through a process called Hawking radiation. Matter itself may decay, with protons, once thought eternal, potentially falling apart. The universe will approach a state of maximum entropy, where energy is evenly distributed everywhere. No heat flows from hot to cold because everything is the same, infinitesimally cold temperature. It becomes a thin, dark, and lifeless soup of diluted particles and radiation, where no work can be done, no structure can form, and no event of any significance will ever occur again. It is not an explosion or a collapse, but the universe falling into the deepest, most permanent sleep. This fate emerges if dark energy is a true cosmological constant, its repulsive strength unchanging. But our understanding of dark energy is so incomplete that a more dramatic end is equally plausible. If dark energy's strength increases over time, we face a far more apocalyptic finale called the Big Rip. In this scenario, the repulsive force does not just push galaxies apart. It grows so powerful that it overcomes every force that holds things together. First, the acceleration would tear apart the cosmic web, separating galaxy clusters. Then, as the force intensifies, it would rip individual galaxies from themselves. The Milky Way would be shredded. Next, the escalating repulsion would overcome the gravity holding solar systems together. Planets would be flung from their stars. Then it would target the stars and planets themselves. The forces that bind a star together, the nuclear and gravitational glue, would be overwhelmed and the star would explode. Finally, in the last moments, the force would reach down to the fabric of reality itself. It would overcome the electromagnetic forces holding molecules together, tearing every atom apart. It would overcome the nuclear forces inside atomic nuclei, shredding protons and neutrons. In the ultimate instant, it could potentially rip apart space-time, the very stage of existence. The universe would end not with a whimper, but with a catastrophic, fundamental disintegration of everything. The choice between a silent freeze and a violent tear hinges entirely on the true nature of dark energy, the same ghost that began dominating our cosmos just as life emerged. This means our origins and our ultimate fate are tied together by the same profound mystery. The quantum seeds of the first instant grew into the galaxies we see, guided by dark matter, only to be ultimately scattered or destroyed by dark energy. The story that began in a burst of unimaginable heat and density may conclude in an eternity of cold stillness or a moment of ultimate rupture. Every fact we have uncovered, from the first fragile molecules to the great cosmic currents, is a single frame in this epic film, whose final scene is written in a language we are still learning to read. From that first quantum whisper to the final cosmic freeze or rip, these 25 forgotten facts reveal a universe of staggering depth and mystery. The simple story of a colossal explosion is just the surface. Beneath it lies a reality shaped by invisible forces, born from a moment before time, and destined for an end we can barely comprehend. We are left not with neat answers, but with profound questions that define our place in the cosmos. We are made from stardust forged in the hearts of vanished giants, living on a planet orbiting an unremarkable star, inside a galaxy being pulled toward an unseen attractor, in a universe dominated by ghosts we call dark matter and dark energy. Every fact we have explored, from the ancient stars older than time to the great silence that surrounds us, paints a portrait of a cosmos far stranger, more violent, and more wondrous than we ever imagined. Our origins are not a single event, but an epic symphony of chance, fine-tuning, and unimaginable transformation. So now we turn the question to you. After this journey through the forgotten corners of cosmic history, which fact reshaped your understanding the most? Was it the universe with no center, the lithium missing from creation, or the terrifying possibility of a big rip? Let us know in the comments below. If you are hungry for more mysteries of the cosmos, be sure to subscribe, and the next time you find yourself under a clear night sky, look up. Remember that you are seeing the light of ancient stars, looking back in time, and standing on a tiny world in a universe whose true story is only beginning to be told.